All right. Well, I think we'll go ahead and get started this afternoon. Well, good afternoon. My name is Kevin Wagner. I'm the director of the Oklahoma Water Resources Center here at Oklahoma State University, and happy to have you join us today for this seminar, this presentation on the Oklahoma Hydrologic and Water Quality System, or OK-HAWQS, as you'll hear it called this afternoon. So our presenter this afternoon is going to be Dr. Srinivasan from Texas A&M University. He is the director of the Spatial Sciences Lab there, but he's one of the developers of not only the HAWQS model that you're going to be hearing about today, but the SWAT model as well that HAWQS is built from. And I've had the pleasure of working with Srini for over 20 years now, and really looking forward to his presentation today. So for many of you that have used SWAT in the past, you well know one of the biggest barriers to using SWAT is really the time and effort required to build the model and to calibrate the model. But HAWQS addresses both of those issues as Srini will present here in a few minutes. So it's our hopes that by making the SWAT model much easier to set up and run, that it can be used more extensively for research here at OSU and at OU and other universities around the state, but also for water planning, watershed modeling, development of total maximum daily loads, conservation planning efforts, as well as educating our students at the universities on this model that's used not only here in the US, but worldwide. This project wouldn't be possible without the support and the guidance of the Oklahoma Conservation Commission, so I want to thank them, and Brad Rogers and Greg Clarkson in particular for their work and their support of this project. And then also certainly appreciate our partnership with Texas A&M University. Want to note that we will be recording the session today. We're doing that so that we can make it available to others that aren't able to participate this afternoon, and in the event that you want to go back and listen to parts of it as well. So it'll be available on our Water Center's website, which is water.okstate.edu. I see everybody's microphones are muted, so please keep them muted during the presentation. But feel free to use the chat to ask questions as they arise. At the end, we'll have a Q&A session, and so we'll go through the chat and try to work through those questions there, as well as you can certainly raise your hand there at the end and ask questions directly of Dr. Srinivasan. So without further ado, I'll turn it over to Dr. Srinivasan.
Thank you, Kevin. Can you all see my first slide, and can you hear me well?
Yes.
Okay. So thanks for the nice introduction, Kevin. And like Kevin mentioned, the HAWQS is a platform or a framework that integrates the model, especially the SWAT model. But in addition to that, it also has got detailed database, computer architecture that helps you to do over the cloud collaborative modeling, so that multi-users and multi-discipline can work together in solving water quantity and quality problems. So I have acknowledged all those groups here, especially the US EPA, who are the main sponsor of the original HAWQS project, the National HAWQS project. And certainly it won't be possible without the Kevin's group, as well as the Oklahoma Conservation Commission, in developing Oklahoma specific version of HAWQS with more detailed input and the calibration and so on, which I'll talk a little bit later. Okay, so with that, So what is HAWQS? HAWQS is a statewide watershed and water quality modeling system, and it's capable of supporting wide variety of state, regional, and local scale economic policy, as well as impact analysis like TMDL or water quality assessment or water resource assessment in general. Some of the water quality parameters that could be simulated through the HAWQS would be the sediment, the pathogens, nutrients, BOD, dissolved oxygen, and pesticides. Some of them are enabled, others is possible to do, like for example, pesticide. We don't have a specific statewide pesticide input, but let's say if you have a watershed, you want to run scenarios of pesticide simulation, you as a user can bring your own input and be able to run using the existing HAWQS system. So it is a nice way of using existing knowledge and adding your own specific knowledge to model a watershed. In more specific terms, HAWQS is a client-server modeling system, meaning it's a web-based, cloud-based technology. You can use it with no GIS experience. You don't have to have any powerful computing systems. You don't have to have any knowledge specifically about the data, how it's integrated and things like that actually. So a lot of those data are done behind the scene on the server side. So you as a user may not have to worry about it. So you can even use your, say, smartphone like iPhone or iPad or any kind of tablet system or a desktop system. As long as you have an internet connection, you can connect to the server, and you don't have to stay on connected actually. You can submit your job, walk away, and you can come back and continue. So I'll be doing a demo, a live demo at the end of the presentation to highlight the features. So it is using the latest, both nationally and Oklahoma specific data set for at a HAWQ-12 spatial resolution. And we are using the NHT plus for the stream network, more detailed stream network, and uses the latest SWAT model. And it uses all publicly available data that can help to set up the model or set up the HAWQ system. This has been going on for quite some time. And of course, Office of Water, EPA Office of Water helped us to develop the HAWQ system. And Texas A&M and USDA ARS are integral part of that. But the national work of verifying and validating and improving the SWAT model came from various other national projects, such as the HUMUS, SEEP. These are all some of the projects that have been going on in decades at Temple, Texas. Okay, and some of you are already familiar. SWAT is a well-known model around the world used for water quantity and water quality assessment. HAWQS has got a very simple GIS interface, just like Google Earth or Google Map, where you can just simple point and click and be able to develop your own watershed at the HAWQ-12 specific. And you could also analyze the data at the farm or field level by examining individual hydrological response units in modeling any watershed or in any field or farms. Okay. It supports all the way from very simple to complex analysis. What I mean by here is HAWQS is going to provide you a framework to do, set up your model, run the system, do the scenario analysis, compare the scenarios like visualization and statistics, and so on and so forth. But HAWQS is not going to mimic what SWAT can do on its own, like a desktop system, for example. So HAWQS allows you to do almost most of your functions or most of your analysis on the server side, but as a researcher, you may want to explore more things that's not available in HAWQS system. So the HAWQS allows you to download the entire data and be able to do much more complex or comprehensive analysis at your local desktop. So the data sets is available both online and offline so that you can build the model and analyze that model inputs and outputs without needing to have additional computing or additional GIS software. For those of you who may not be familiar with SWAT model itself, I have few slides to go through that very quickly. And I know some of it may be repetitive for some of you. Please bear with me. So SWAT has got various major landscape process. The main strength of the SWAT is the landscape processes, where the weather drives your hydrology, your comprehensive hydrology, which you will see in the next slide, and erosion and sediment process, both landscape and the river process, sedimentation process, the land and soil management in terms of crop management or vegetation management, or looking at tillage, pesticide, fertilizer, and so on and so forth, and the nutrient cycling, including carbon and bacteria, is included in the model. So this gives you a comprehensive overview of how SWAT deals with hydrological components. Like rainfall is the only input here, then you need to tell what vegetation is growing on this soil, and the SWAT model will give you outputs such as how much is the evapotranspiration, for example, how much is the runoff, how much is the lateral flow, how much is the return flow, how much is recharged to the groundwater, and so on and so forth. Okay, so it has got sets of equations that governs each of this process, and you'll be able to get output from each of the intermediate variable as well as the final variables. Okay, again, I'm not planning to go through every one of them. Just to give you on the hydrology, we do take into consideration of the canopy storage and infiltration, evapotranspiration. We have 3 different sub-modules within evapotranspiration to use, such as Penman, Hargrave, or Priestley-Taylor method, and so on. It has got subsurface flow and surface runoff, base flow and return flow, channel characteristics like channel loss, channel evaporation, ponds and reservoirs also can be modeled. So one of the major strengths of the SWAT is the crop or vegetations that you can simulate and able to verify and validate crop biomass or crop yield, and thereby you are able to validate the nitrogen and phosphorus uptake by the plant and the nitrogen water phosphorus balance in the soil and so on. And also it has got a very detailed land management just as listed here. SWAT has been in development. If you want to know more about the SWAT itself, you can go to the swatmodel.tamu.edu website. It's in development for well over 50 years. And it's been well adapted worldwide with many projects and verified and validated. We have more than 4,300 peer-reviewed publications, and our average publication per year is about about 500, which is about a 1.5 per day is our number of publications using SWAT model around the world. Actually, we do conduct a lot of conferences and workshops if you are interested in getting in more detail with SWAT model. So specifically in the OK-HAWQS, we are simulating all the urban landscapes, the ag lands, that includes the managed and unmanaged pasture and rangelands, forest, woody biomass, as well as wetlands and any kind of barren land and so on. And in the stream processes, it takes into account of all the stream channel morphology, geomorphology, the ponds, reservoirs, and wetlands or model. In the agronomic practices, we're looking at the crop rotations. We are using the crop data layer of 2016, 17, and 18 to look at the crop rotations. And those crop rotations are included the crop residues, the tillage, the fertilizer. The pesticide is capable of inputting pesticide, but we don't have specific inputs yet. And if there are irrigation, we do take into consideration of irrigation. And infill conservation practices, you can simulate various tillage practices, tile drains, if you have the tile drains, grazing management, or grass waterways, and so on. We can also do the edge of the field buffer practices like filters and riparians and field borders and so on and so forth. Actually. So what is HAWQS and what is SWAT actually? HAWQS provides you an automated way to process the SWAT inputs based on internet-based interface, meaning a web-based interface. It's most efficient. When I show the demo, you'll see within few minutes, you'll be able to set up a watershed anywhere within the state of Oklahoma. And you need only a minimal computing requirement. You don't have to have a very heavy equipment, and you don't need to worry about having all the software license and everything. Everything what you'll be using is public domain based information. And you can have multiple users accessing simultaneously the HAWQS system. So you're not worried about having only one user access or limited user access. And the most importantly, in the most updated HAWQS system, we do have sharing of models. So if you have a hydrologist who could be verifying and developing a model for hydrology, then there could be a water quality specialist or an agronomist or a soil scientist can look at the water quality aspects, because SWAT deals with multi-dimensional or multi-discipline fields of expertise. So you could be working in a collaborative, so you can set up a project and share that within your group, and they all can have access to the same model while they are developing their scenarios or checking the model results and so on and so forth. Actually. So this is what will be set up for the HAWQS Oklahoma. We have about 3 segments here. Actually, I don't know if you're able to see them very clearly. This region here, which is mostly the Arkansas River, there are about 1,753 HAWQS sub-watersheds. The southern one, which is mostly bordering between Oklahoma and Texas, that's about 781 HAWQS here. And there are few that's originating right at the eastern end of Oklahoma. There are about 71 of them. In total, there are about 2,600 HAWQS watershed that comprises the whole state of Oklahoma. And the green dots are the gauge locations where we have planned to do calibration for hydrology at a monthly scale. And that calibrated model setup is what's available, so that anywhere when you run the model, you have a calibrated model for hydrology is set up before you can even start any scenarios and things of that nature. And the red triangles are the existing major dams that will be incorporated in the system also. So there are about 48 major dams and about 42 calibration sites we are planning at this time. Here are the list of data sets. I don't expect you to go through them. The major differences here I want to talk about the national versus here is the crop data layer is based on the CDL and NLCD 2016. And the soil is based on SURGO, soils map, whereas national project, national is StatsCo. And of course, here is the land use, NLCD 2016 and the CDL 2016 and 17 and 18. And we will have 4 sources of weather data that one can use to set up the model, actually. The PRISM, the NextRad bias corrected, as well as Oklahoma Mesonet data set. So what can you use the HAWQS for? HAWQS could be used to evaluate the land management, crop management, such as fertilizer, tillage, irrigation, crop rotations, conservation practices, or pollution control, whether it's a point sources or non-point source, or load allocation or source allocations. You'll be able to do a lot of them actually. And you can also look at climate change or climate sensitivity or climate resilience, whatever the terminology you're more comfortable with to do any climate scenarios. So these are all, I listed a few other applications that's already been used in the national HAWQS for. Most of them are weather-related scenarios or conservation practices or CAFO operations, benefit assessment. A lot of the time, people who are using a HAWQS system are non-hydrologists and water quality specialists used for economic and environmental type of ecologists use the model to look at the impact of water quantity and quality on ecology or environment or economic impact and so on and so forth. And of course, there are lots of regulatory and policy implications has been assessed with this system also actually. So just to wrap up, the HAWQS using public domain databases, tools, and technology, including output visualization, no GIS software or knowledge required. It's a standard assessment through a web architecture, or more complex analysis with additional desktop tools could be done. And one of the analysis that was done shown more than 90% reduction in time and effort to put together a modeling system for an assessment. Okay. In other words, if you look at a lot of the time, either if it's done for an academic research purpose or for consulting company or anybody else, actually, it takes them anywhere between 1 to 2 months just to process all the input and get the inputs ready before they can even run the model, leaving alone calibration, validation, and stuff like that. Here you are going to have your data set that's with the most updated, most detailed available database, including flow calibration for the whole state will be ready, and you should be able to run the model anywhere in the state of Oklahoma within a few minutes, actually. With that, let me stop right here and jump into the online system to give you a live demo of the HAWQS system. Okay. Sorry about that. So what I'm demonstrating right now as an example, the interface looks very similar to what you're going to see today, but the database, the calibration model, and everything will be for Oklahoma HAWQS. Okay. So this is obviously a national HAWQS, just to give you a preview of what it will be actually. So if you want to create a new project, this is my desktop here actually. I'm logged into through Chrome to the server, HAWQS server. And let's say I want to create a new project. I simply click create a new project. And I'm going to select for Oklahoma HAWQS, we are going to have the data available by HAWQ12. And I should be able to zoom in anywhere within the state and be able to select, let's say if you want to model this river here, and I can simply click on that river, it'll automatically draw all the HAWQ12 boundaries upstream of that actually. But I'm not required, or I don't have to, even though now you can see this goes all the way into Colorado and so on and so forth. So I don't have to model everything here. Let's say I want to model only from somewhere along the river. Let's say there is a dam and you want to model only from that. I can simply go here and I can go to the advanced option and I can say, okay, I would like to begin my modeling only from at the border right here actually. Let's say this is your starting point in Oklahoma. Then I can say simply select that, click on that subbasin, and I say done selecting subbasin. So it will automatically truncate everything upstream of that, and that will be a boundary condition to start your river. From there, your outlet. Okay, so you can interactively select the area that you want to model. Just because I'm going to do a simple demo, I'm going to choose a smaller river. Let's say I'm going to select something like this one. Oops. I zoomed in too much. Okay. Let's say I want to model whatever that's flowing into this lake, for example. So it shows you the area that is draining into that lake. And you can also see the name of the creek and so on and so forth. This is what we want to model. I select that. And if you want to look at the routing, how the water is going to get routed, you can also see that on the screen itself. Or if you want to look at the view, you can also look at it. There are 12 sub-watersheds here, 12 HAWQ12 boundaries with 716 hydrological response unit, which is nothing but overlay of land use, soils, and a slope map. So let's say I want to create this project. I click create. So now I'm creating a project for just that region that I just selected here actually. Okay. So you can interactively select that. And then I'm ready to set up my HRU. The size of the watershed is about 1,200 square kilometer with 716 hydrological response unit. I can look at the what are the distribution of land use here actually. Okay, so when I click on the HRU, it's going to show me what are the different land uses. What are some other dominant one actually? So you can see about 62% is rangeland, and about 24% is winter wheat, and then about 4% is urban. If you want to protect any of these land uses, you can protect them actually. Just because they are very small, they don't have to be like cotton, for example. Cotton is only 0.112% of this watershed. And if you felt like cotton is an important crop, you are going to simulate some pesticides, thereby cotton is important, you can just select this. That means it will not be subject to any elimination. So anything that you check here, that means don't remove that land use or don't remove that HRU. Okay, you don't have to remove anything actually. I can set up this to 0, thereby I can model all the 716 HRUs. But sometimes, because when you overlay the GIS layers, you may have some sliver polygons like 1 or 2 pixels that you may say you don't want to model that 1 to 2 pixels actually. So you can set up threshold, like say set by area or by, you can target number of HRUs. Okay, you set by area, you can say, okay, I want to consider at least a minimum of 1 square kilometer. That means out of the 1,200 square kilometer, if your HRU is not even 1 square kilometer, it will remove that HRU and aggregate with the rest of the watershed. We are still modeling the same 1,200 square kilometer watershed, but it will remove the smallest polygons or smallest area that is less than 1 square kilometer and aggregate that to the rest of the rest of the HRUs, so that by proportion, when I say proportion, it's proportionate based on what is it actually, what is the weighting factor? The weighting factor is the percentage of the area that occupies the land use in that subbasic. So again, this is only optional. If you don't want to use this step, you can directly use all the 716 HRUs. So let's say I save the changes. So it's done. So now it eliminated about 573 of them are less than 1 square kilometer, and it did protect the cotton landscape, and thereby the new, this is the original distribution, and this is the new after you apply the threshold. So if you look at it, 62.8 was range. Now that's become 67.9. There are a few percentage points has increased because of the lot of small, tiny polygons due to the overlay of land use and soils and slope maps. Okay. Again, if you don't approve of this, you can reset the threshold, go back and redo this analysis if you want. This is just a demo, so I'm going to go ahead and accept this and say create my scenario. So here is a scenario that's going to develop. You can name anything you want, and then you can choose what weather data that you want to choose to run your model. Okay, let's say I want to run Prism, for example. Okay, and the Prism data set is from 1981 until 2018. We'll have to until 2019 shortly. Let's say I want to run, you don't have to run all the 38 years. You could say I want to run from 2008 to 2018, for example, the last 7 years. Sorry. Okay. So you can choose only, or you can just click on here and you can do it a calendar mode also. Actually, I'm just typing it directly. And you can set up your warm-up period, however many years you want to set model setup period. That means the SWAT model will not provide you output for 2008 and 2009, and it will give you output only from 2010 to 2018, depending on how many years you are considering as a warm-up period or setup period. And it's going to give you daily output, or you can ask for monthly or annual output. And you can also choose which version of the SWAT model you want to run. So one of the nice things about the HAWQS system is the entire system, entire modeling is online, archived. So you don't have to worry about saving your project or anything like that. Let's say if people move from job to job, and if you are in a company, consulting company, and somebody has moved, the project still stays on the system. So thereby you could easily go back and be able to reclaim that project and able to do an additional analysis. Let's say 5 years from now, you want to do additional analysis, another project, another scenario, you don't have to build from scratch. You can go back and dust off the old project that you created and able to even run the old version of the SWAT model if you want to, and then able to run scenarios. So that's another nice thing about this is it's all completely archived and reproducible results, which is one of the requirements for any water quality and watershed project. So once you set up your baseline, in the model inputs for the time period you want to run, and what weather data you want to choose, how many warm-up period and daily output, and what version of the model. That's all it requires to set up the model actually. Now I can say run my scenario. Before I showing the running scenario, I also want to show few inputs that you can customize. For example, you can customize the basin level input data set. You can go in here and you said, oh, okay, I don't want to use Penman method actually, and I really would like to use Hargrave method, for example. You can change it. You can change your evaporation factor if that's an important to you, okay? Then whatever changes you make, you click Save Changes, that change is made. One of the nice thing about the HAWQS is it keeps track of every change you make as a metadata. So when you export your metadata, you will see how the model was built and what are the changes were made, so that it becomes a history of all the information that you made. So that again, going from one user to which you're going to share models, everybody knows what was done to that inputs to generate or to create that model. So you can do the same thing in other inputs here, or I can go back, and if I want to change my curve number in the model, I can simply go to curve number and I say, okay, I want to increase the curve number by 2%. You can do that. You can apply to all HRUs or specific HRU. So when I say specific HRU, you can select, okay, where exactly you want to make the changes, which subbasin. You want to apply to that subbasin, only that subbasin will be selected here. Or you could select multiple subbasin, for example, okay? And then within that, you can also select what land use you want to apply, what soil, what slope. So you can go and change input on a specific hydrological response unit or specific landscape or to the entire watershed, depending on your input choice that you want to make changes. I'm just trying to show you this as an example here. I'm not going to make the changes right now, but I'm trying to show you how you can edit and customize your input to the level of detail that you are interested in actually. Same way we have sediment routing methods, point sources. You can update your point source, your own point source. You can also do land use update, meaning change the land use over a period of time. You could start with certain land use in 1980s, and you can update the change in land use in 90s and 2000. And so you can have a dynamic simulation as the land use changed from over a period of time actually. And you can change your urban data, fertilizer data, and so on. You can also change any of the ag operation like tillage, fertilizer, pesticides, and so on and so forth. You'll do it through here actually. In the interest of the time, I'm not going to go through that right now, but later we are planning on having a full-blown workshop of using OK-HAWQS. So at that time, we'll be able to run various scenarios, building a model and so on actually. So I think we are expecting sometime in March, April, springtime, we will have a follow-up, a full-blown workshop, a day long or a half a day to 3/4 day long workshop to go through this inputs and go through the various scenario building and so on and so forth. Okay, let's say you are ready to run the model. So you can say run. Yeah, my mouse is very sensitive. Give me 1 second. Okay. So it gives you a rough time. It's going to take you about 4 minutes. I don't think it will take that much time. So you can see this next option is edit tables, right? If you choose this option, you can download the data and run offline. That's the only reason you want to choose this option. If you're not going to do that, you don't need that. And also I told you that you can click here to email you every step of the process so that you don't have to wait on the screen for that process to complete. Let's say you are going to do something that's going to take 20 minutes. You don't have to wait on the screen 20 minutes. Actually, you just submit the job, walk away. It'll send you an email when it is done. Since this is a small enough watershed, I'm going to go ahead and accept it. And you can see this is starting to write the inputs, and it will start to run the model very quickly following that actually. So it's right now executing the model. Now there was some question. Maybe I can try to answer that question while that's running. Okay, are the initial default inputs related to the geography selected for the analysis? Absolutely, yes, because these are all geospatial data set, like your land use map, your soils map, and your weather inputs. Everything is geographically specific data set. So all the data will be based on that geography, wherever the watershed that you're simulating. In addition to that, since we are calibrating based on 42 gauges, what you're getting, the initial parameter is already a calibrated model for that level of calibration. It may not be calibrated on every edge of the farm or every small watershed, every HAWQ12, but based on the available USGS gauging station, we are attempting to calibrate for a long time period. And that will be the basis for the input in the HAWQS Oklahoma version. Thereby you will, when you set up your model, you are getting a calibrated model for hydrology. Few more minutes to, it's calculating all the statistics and so on and so forth. Thereby it will be useful to do the analysis. If there are other questions in the meantime, you can throw in the chat box. I'll be happy to share with you actually. How about coefficients? Coefficients is part of the calibration parameter, right? So when you calibrate like evaporation coefficient, if it is calibrated for hydrology, you will get that calibrated model output actually. Can soil health practices such as cover crops, no-till can be modeled? Absolutely yes. So that's what I was showing you about the ag practices. So under the ag practices, you'll be able to run them and then able to compare the two different scenarios, the current and the no-till scenario, for example, and look at the impact on soil nutrients or soil organic carbon, or look at the sedimentation process and so on and so forth. Are there online training for this program? For the HAWQS, we do have help section actually. When you go to this help section, you do have some training videos, as well as PowerPoint and documentation and so on and so forth. It's extremely well detailed documentation is available there actually. And as we complete the Oklahoma HAWQS, we will have similar kind of thing detailing about how the data was processed and how the calibration was conducted and what are the calibration statistics. All those things will be provided as part of the modeling system so that you will be able to evaluate whether that's good enough or you need to even calibrate further, or you have to use some assumptions, different assumptions. You will be able to choose how you want to use the system. Okay, I think it's finished. Oh, it's still running. Let's see. Oh, it's finished, yeah. Okay, so the model has run for the 11 or 12 years. Now we are ready to analyze the output. So when I click on the output, I can run SWAT check. Those of you familiar with SWAT model, they may be familiar about the SWAT check program, which is nothing but a 30,000 foot overview of your watershed, actually, watershed analysis. So we ran the model for 11 years with the 2 years warm-up period for 143 HRUs with 12 subbasins, about 1,200 square kilometer watershed. Let's look at the hydrology. So here is the hydrology. The average rainfall in that region is about 700 millimeter for that period of 11 years that we ran the model. And the average evapotranspiration is about 492 millimeter. And the average current number used in the watershed is about 64. And this is the runoff, lateral flow, return flow back to the river. Okay. You can also change the units if you are more familiar with the inch system, English system. You can change these units actually in your user settings, account and group settings. You can go to your account and you say, I want the model. The model will always run on metric system, but you can convert the outputs into an English units if you are interested in seeing the outputs in English units, more familiar with that than metric system. So this gives you about 70% of your rainfall is ET, about 25.4% is stream flow. Of the 25.4%, 66% is base flow, and 33% is the runoff in this watershed. Okay. And if you want to look at the same data on a month by month, you can click on the monthly values. Here is your rainfall distribution for the 11 years on a month by month. How much was the snow? How much is the runoff? Lateral. Water yield is nothing but your stream flow. These are all expressed in depth in millimeter. Okay. And sediment yield, nitrogen, and so on and so forth. If you are interested in looking at things like sediment, click on sediment tab. It gives you average annual, how much sediment in megagrams means tons per hectare. So it's 0.2 tons per hectare. Okay. And how much is the contribution from the point source in this watershed? And how much of them is either deposited or scouring happening in the channel? When you say negative number, that means you are getting eroded. Your channel is getting eroded. If you get a positive number, your sediment is getting deposited. Okay. And you can also look at the nitrogen cycles, phosphorus cycles, plant growth, like biomass, crop yield, and so on and so forth. Or if you want to look at the losses, let's go and look at it here in the interest of the time. How much is the nitrogen loss, for example? Total loss of nitrogen in the watershed. Of that, how much is the organic nitrogen? How much is the soluble nitrogen? How much is leached to the groundwater? How much is gone through the lateral flow? How much is in the groundwater? So you can get the entire configuration, composition of your nitrogen species or nitrogen components in the watershed. This is for all the watershed. Later, you'll be able to get the data for a specific HRU, specific land use, specific subbasin, specific river reach. You'll be able to get the same information. So same thing for phosphorus, total phosphorus, organic phosphorus, soluble phosphorus, and so on. And you can get more detailed information. As you can see here, there are more other informations. Like one of them that may be of interest to you is the point source, for example. So how much is the total flow from the watershed? Of that, how much is the point source? And thereby you can see point source contributes about 2% of the flow. On the sediment, how much tons per year? How much is the point source? That's about 0.6 tons per year, for example. So same thing for nitrogen and phosphorus. So if you're looking at load allocation in a TMDL scenario, this will be useful for you to see what portion is coming from point sources and what portion is coming from non-point source, and so on. Okay. So let me jump back to show you a few other tools. Then I wanted to allow you to ask more questions for me. So you can also create maps. Okay, I don't have the time today to show you the comparative chart. If you run multiple scenarios, you'll be able to put maps side by side to show them before and after. Okay, same thing on chart. You can do comparative charts. So let's say I want to show the subbasin output. What statistics? Let's say I want to look at the average annual and what parameter you want to plot. Let's say I want to look at the sediment yield. I mean, I'm just picking out, and if you can choose whether you want to display in imperial or metric units. Okay, like English units or metric units, and you say, get me a map. So it'll show you how much is the average annual sediment. So here is the scale. So if you move your cursor, it'll tell you it's 0.03 tons per acre, it's 0.06 tons per acre, this is 0.18 tons per acre, and so on and so forth. You can change the color. You can just click on this here, change the color. You can export this into PDF. And you can print it directly. You can save it as a PNG image or JPEG image. So you can download the data as a comma delimited file. So you have all kinds of options to customize your output in a way you want it actually. And you can print them all together. Okay. And if you had the multiple scenarios, I could have chosen both scenarios and I showed you the map side by side. It'll plot all of those outputs. Or let's say you want to look at the time series data and I want to look at chart. And I say what's happening in the river, reach output. And I say I want to look at the flow. And I want to look at, say, sediment. And I want to create as a new axis, add an axis. And if I want to look at total nitrogen, let's say, for example, total phosphorus, again, you can choose your units. I can choose multiple axes. And what statistics, let's say I want to look at the monthly. You can also do load duration curve, LDC, flow duration curves. You can do all those stuff here, or box plots. You can select where exactly you want to look at by picking the subbasin number, or you can just click on the map. Okay, I want to look at the output of the watershed outlet and maybe somewhere in the middle, for example. So I also want to look at right here. So I can have multiple location I can choose, and I can say, get my chart. So here is the value at that location. And you can also change your axis from linear scale to log scale and so on. And shows you the flow in cubic feet per second because we use the English units, and sediment out in English tons, pounds of nitrogen, pounds of phosphorus. If you don't want any of them, you can just simply click on it to disable that actually. And you want to look at the flow of nitrogen, you can just look at the flow of nitrogen, for example. And again, you can export this data, you can export this map, you can print it, you can download the image and so on, so forth. You can also zoom in for a particular thing. You can get into much more detailed output by zooming into that map. So there are lots of features, not only to build a model, visualize, analyze, and compare different scenarios and so on and so forth, actually. In the interest of the time, let me stop right here and maybe answer more questions. And I'm sure later we're planning on doing a more detailed workshop that will help you, but also you can play around with the tool as time permits in the meantime. Kevin, is it a good time to stop myself and maybe I'm allowed to answer questions?
Sure. I see you've already got another question in the chat.
Export table of input data used in the analysis, for example, time series of total phosphorus. Absolutely, yes, you can do that very easily. The map that the plot that I showed you, you can pick and choose anywhere in the watershed and say, plot that map. While it's plotting the map, you can also ask to export that map or export that plot or export the actual data that's coming off of the modeling system. Yes, you can do that.
So Srini, I've got a question. So dealing with future climate scenarios, is this tool equipped to bring in some of those as well, or do you have to do that offline?
Currently, the national database available for climate change models are only at the level of 8 and 10-digit watersheds, not at the 12-digit. In other words, downscaling to a 12-digit is not advisable yet because of the uncertainty it poses actually. So what we could do is, I do have about 12 models that has been already downscaled and projected for next 100 years with different scenarios, RCP scenarios, 4.6, 2.6, and say 8.0 and so on and so forth, 8.5. So we can take those models, they are applicable at the HUC 10 level, but we can apply it to the same, to all the HUC 12 within a HUC 10, for example, and be able to run the model. So that feature is already available, and we could certainly, that data is already available. We can try to bring that in here and make that as one of the scenario feature that user can choose to run climate change scenarios and so on.
Okay.
Can the user, one of the questions online is, can the user augment the input data with their own data? Yes, it's on a limited basis. For example, with the online data, if you take the whole model offline and do it on your desktop, then you have nth degree of customization. You can change any inputs, you can add your own inputs, and so on. However, if you're going to add your data onto the existing online system, we can update land use change, we can update weather input, we can update point source input, for example, and you can obviously you can change land management and so on and so forth. So I need to know a little bit more specific exactly the type of input that you're thinking, whether that's allowed or not actually. But right now we have a limited set of user input that can be updated as part of running scenarios. Any other questions, comments, feedback? You can unmute and talk also, actually. You don't have to type on the chat box if you want to ask questions.
Well, if there are any other questions, definitely feel free to contact us and let us know. So the time frame for getting the OK-HAWQS online and ready to use should be late this spring, certainly before the end of May. And like Dr. Srinivasan said, we plan to have a one-day training session sometime before the end of May as well. So once the tool is up and ready to go, we'll be having a training to go through each component of the HAWQS model and allow you as users to give it a try on a test watershed and just to get a better idea of its capabilities and ask the questions that you might have. But as you can see, it's very much user-friendly, especially compared to SWAT. So I think it's pretty exciting to have access to this tool and to have this tool calibrated for Oklahoma. Are there any other questions out there or comments? Well, if not, we really appreciate your participation today. Dr. Srinivasan, thank you so much for your work on developing this tool and for the presentation. And expect a follow-up email from us. We want to get some of your feedback and comments, ideas for maybe other aspects of the model that you may be interested in improving, or maybe some specific scenarios that you'd have interest in running. So we'll be sending out an email before the end of the week to get some more feedback from you. But thanks again, everyone, for participating. Thanks, OCC, for sponsoring this work. And thank you, Srini, for your presentation today and for your work on HAWQS.
Thank you. Appreciate it. And yeah, as Kevin said, we are looking forward to your feedback to continue to improve and continue to make the tool more usable and useful to everyone. Thank you very much for participation.
All right. Have a great rest of your day.
Okay. Bye.
All right. Bye.